This is example 4.2-7 from the text Conceptual Dynamics. The problem statement reads, in the following figure, mass C is attached to a rope that is wrapped around the outer edge of drum B. As mass C falls, the rope around the drum unrolls without slipping, causing the drum to rotate. This in turn causes pulley A to rotate due to the belt connecting the drum's inner radius and the pulley. Consider that mass C is released from rest and reaches a velocity of 1 meter per second after it has fallen 30 centimeters. If the mass accelerates at a constant rate, find for the instant shown, A, the magnitude of the acceleration of point P on the outer surface of the drum. So after reading the problem statement and looking at the figure, we try to understand what's happening. This is a pure rotation problem, rotation about a fixed axis. We have these two pulleys that are purely rotating about their center, about an axis through their center. Beyond that, it is also a constrained motion problem or a dependent motion problem because of the belt connecting these two pulleys. The rotation of one will correspond to the rotation of the other. And furthermore, the fact that this weight, this mass, is connected via a rope that unwinds without slipping means that the motion of mass C will also relate to the rotation of this drum. So once we sort of understand what's happening, mass C falls, and as it falls, the rope pulls this drum around, and then the movement of this drum causes this belt to move, which then in turn causes this pulley to move. Once we understand what's happening, we then try to identify what's given and what's unknown in the problem. So we see that mass C is released from rest. So that means its initial velocity is 0 meters per second, and it reaches a velocity of 1 meter per second. So that's its velocity at state 2 after it has fallen 30 centimeters. So that mass C displaces 30 centimeters, which is the same as 0.30 meters. So this block is initially at some height, it falls, and as it falls, it accelerates from 0 to 1 meter per second. We're also told that the mass accelerates at a constant rate. So we're not told explicitly what the acceleration of mass C is, but we know that it's constant. We're given this information, and we're going to be asked to find a few different things. The first one of which is the magnitude of the acceleration of point P. So here's point P, and we want to find the magnitude of its acceleration. So now that we've sort of set the stage for the problem, determined what's given and what we want to find, we can actually commence with a solution. Moving to this next page, we've recopied everything that's given and what it is we're trying to find. So ultimately, we're trying to find the magnitude of the acceleration of point P, where this is point P. Point P is on the outer edge of this drum, and it's moving basically in a circular path at this instant. And so since we know the path that this particle is following and it's a curved path, we're going to use NT coordinates. So we'll have the tangential direction, which is tangent to the path of motion of the particle. Then we'll have the normal direction perpendicular to that pointed toward the center of curvature. And so in order to find the magnitude, in essence, we need to find the tangential component of the acceleration of that particle and the normal component. Where the tangential component is the rate of change of the speed of the particle along the path. And the normal component is equal to its velocity squared divided by rho, the radius of curvature in the normal direction. So we're not given very much information about point P directly. Most of the information we're given about mass C. However, the fact that mass C is connected by a rope that is wrapped around the drum and unwinds from the drum without slipping means that the motion of P is related to the motion of C. Specifically, however much point C moves downward, that's exactly equal to the displacement of point P along the curve. And so since they experience the same displacement over the same amount of time, that means that they have the same velocity. So the velocity of point P is equal to the velocity of point C at any instant. And similarly, since they have the same change in velocity over the same period of time, they also have the same tangential acceleration, or more specifically, the tangential acceleration of point P is equal to the acceleration of mass C, because mass C is moving in a straight line. And so if we can figure out some of this information, then that tells us about the motion of point P. So we're supposed to determine the magnitude of the acceleration at the instant shown, that is when VC is 1 meter per second. So that we have directly. We're not told what AC is explicitly, but we're given displacements and changes in velocity and told that the acceleration is constant. And so that's a sufficient amount of information to determine what AC is. Since AC is constant, we can use one of our constant acceleration equations, or we can fall back to our general equations and perform the integration. Thinking back to the different kinematic relationships we've been using, in particular for rectilinear motion, this is the one that's most suited to our problem because we're not explicitly given any information about time, and we don't need any information about time. And so this relationship relates acceleration, which we're trying to find, the displacement, which we know, and the velocity, which we know. Okay. So this is a good choice. So we'll go ahead and this is all for sort of particle C. Again, we sort of keep in mind that the tangential direction of motion can be thought of as a rectilinear problem. This particle isn't moving in a straight line, but it's moving along a path that could be described by a single coordinate. And in that sense, it can be thought of as a rectilinear motion problem. We can integrate, say that the initial position is 0, keep some variable final position. The initial velocity is 0. We'll leave it as a variable upper limit. Since AC is constant, its antiderivative is just AC times S. C. We evaluate it at the upper, subtract the lower, which is 0. On the right-hand side, the antiderivative of that is 1/2 VC squared. Again, evaluated at the upper limit, subtracting the lower limit, which was 0. We get this expression And so we solve for AC. There we get an expression for the acceleration of point C. We specifically want to know the acceleration when the mass reaches 1 meter per second after it's fallen 0.3 meters. So we substitute those values, 1 meter per second, square that, 2 times 0.30 meters. 1 divided by 0.6, if we round, it's approximately 1.67. We have meters squared per second squared divided by meters, so that meters cancels one of the meters. We're left with meters per second squared, which is what we would expect for an acceleration. So that gives us our tangential component of the acceleration of point P. The normal component we get by squaring the velocity and dividing by the radius of curvature. So at this instant, we know that point P has a velocity of 1 meter per second. If we look at the radius of curvature, so this point P on this outside of this drum is going in a circular path centered around the center of the drum. And so the radius from the center of the drum to its outer edge is 1.2 meters. It's a little obscured, but you can see it there. So 1 squared divided by 1.2 is approximately 0.83 if we round. Again, we have meters squared over second squared divided by meters. This meters cancels one of the meters in the numerator. We're left with meters per second squared. Okay. So now that we know the two components of the acceleration of point P, we have its total acceleration, 1.67 in the tangential, 0.83 in the normal, approximately units of meters per second squared. We ultimately want to find the magnitude, so we can find that using the Pythagorean theorem. We take the one component, square it, take the normal component, square it, add them together, and take the square root of the sum. And we get that the magnitude of the acceleration is approximately 1.86 meters per second squared. So that is the solution to the first part of the problem, part A. Moving to part B of the problem, we are then asked to determine the angular velocity and angular acceleration of drum B. So we want to find angular velocity and the angular acceleration of drum B, where it's rotating sort of in this direction. So looking at this, the fact that we have pure rotation, fixed axis rotation, and we know about the motion of point P on the rigid body, we can relate the motion of point P, its velocity and acceleration, to the rotation of the drum. So thinking back, the velocity of point P is equal to its radius times the angular velocity of the body, which is omega b. We know what the velocity is, we know what the radius is, so solving for the angular velocity of the body is simply a matter of dividing through by the radius. It's the velocity of p divided by the radius. From the previous slide, we have that the velocity was 1 meter per second, the same velocity as mass c. And then we have the radius at which point P is moving as 1.2 meters, the same as rho, the same as the radius of curvature of the path. One divided by 1.2 is approximately 0.83 when we round. The meters cancel, and so we're left with units over seconds, and implicitly that's radians per second. Radians is kind of a non-unit. So that's the angular velocity of the body of drum B. Similarly, the tangential acceleration of point P is related to the angular acceleration of the body via the radius. And in order to solve for the angular acceleration, we can simply divide through by the radius again, since we know what the tangential component of the acceleration of point P is from the previous part of the problem, that the angular acceleration is equal to the tangential component of the acceleration divided by the radius. The tangential component of the acceleration was approximately 1.67 meters per second squared. Same radius, 1.67 divided by 1.2 is approximately 1.39. The meters again cancel, leaving us with something over seconds squared, and it's implied that it's radians per second squared. So that gives us the angular velocity and angular acceleration of drum B. The last part of the problem asks for the angular velocity and angular acceleration of the pulley. And the fact that this drum is connected to this pulley via a belt, and we'll assume that the belt is not slipping, means that the motion of any one of these points on the belt are constrained to move together. For example, whatever distance this particle moves in a given amount of time, that's going to be equal to the distance that all other points travel at a given amount of time, including a point on the perimeter of pulley A. And so based on that fact, since they cover the same distance in the same amount of time, they'll have the same velocities. So, if I'll just consider the belt velocity to be the velocity of any point on the belt. So that's always going to be equal to the radius times the angular velocity of drum B, and it's going to be equal to the velocity of a point on the perimeter of pulley A, where it has a radius and angular velocity. So if we want to determine the angular velocity of body A, we can take this relationship and divide through by RA. So we have that the angular velocity of body A is RB divided by RA times omega B. In this case, RB is going to be 1.0 meters because that's the radius of the inner drum that the pulley is connected to. So RB is 1.0 meters. RA, where the other side of the pulley is connected, 0.5 meters. And omega B is approximately 0.83 radians per second. And so the angular velocity of body A will be twice the angular velocity of body B. And that works out to be approximately 1.66 radians per second. If we carried out more decimals, we would round to 1.67, or we could consider it to be 1.66 repeating. Similarly, just in the same manner that any point on the belt had the same velocity, they also have the same tangential acceleration, since they have the same change in velocity over the same increment of time. So we'll call that the acceleration of the belt, or the tangential acceleration of any point. It's equal to the radius, the angular acceleration of body B, the radius of body A, times its angular acceleration. If we want to determine alpha A, we divide through by RA. And so again, the angular acceleration of body A will be twice the angular acceleration of body B, where body B had an angular acceleration of 1.39 radians per second. We multiply that out, we get that the angular acceleration is 2.78 radians per second squared. And that brings us to the conclusion of this example.